All right, section 2.2, we're going to take a look at something called a set and how we can describe it. So first, just definitionally, a set is simply a collection of objects. And those objects are called elements. These objects can be anything you'd like. It can be the contacts in your phone. The set is contacts in your phone. Each person in that phone, that contact is one of the elements. It can be the classes you're taking this semester, right? That's a set of classes, and each individual class is an element in the set. It can be a group of numbers, which is what we're going to be focusing on mostly. But you actually see sets used in really young kids without numbers. They tend to work with more things in terms of categories. In fact, I remember my daughter coming home in about, I think it was second grade. It might have been third, but I'm pretty sure it was second grade. And doing something, I don't know if it's something we're going to do today or on Monday or Wednesday, but within these section 2.2 and 2.3 that I didn't know would show up quite that way in her classroom. And it was related to sets. So when we get to it, I'll mention to you what it was so that you can see how I have seen it recently-ish used in a younger child's classroom. All right, so there's two ways that we're going to describe sets. One is the listing or the roster method. So what the listing or the roster method does is literally lists everything out. So if you imagine like a roster for a class, like I have a class roster for this, it just lists everyone else's names out, okay? Got your name on there and your ID number. Okay, there's a couple other pieces of information, but the point is that it is representing you in a list form. Okay, that's the listing or the roster method. So we're going to do one where I can write it down in terms of some numbers so I can show you the difference in these. So if I had these numbers, they're put in these curly braces, right? And these curly braces indicate that I have a set, and the items that are listed inside there, 1, 2, 3, 4 in this case, are the elements. So the set is everything. The individual numbers are the elements. And this is a list. So it's a listing or the roster method. Now, set builder notation tends to work really well if this list were very long. If I have a list from 1 to 4, I'm going to write it like that. That just makes sense. But if I have a list from 1 to 50, I don't want to write down 1 to 50, right? That would probably not be the best use of my time. There's got to be a shorthand way, right? It's a shortcut way of writing it. Now, you may not like my shortcut way of writing it, but it is the one that's typically used in mathematics. So I'm going to show it to you. We're going to start with a curly brace. So both of them have curly braces. And we're going to list, usually people use the letter X, but you could use a different letter if you want. So write it X, and you're going to draw a vertical bar. Okay? I'm going to write the rest of what I'm going to be down, and then I'm going to explain it. Okay? So we're going to say that X is less than 1. I'm sorry, 4, 5. Let's do 5. X is less than 5. And we're going to say X, we'll write it this way for now, is a natural number. There's more than one way to write this. This one will work. Now, the notation for this is kind of weird looking because I'm about to change it into something weirder in a minute. But let me tell you what this is saying. This piece at the beginning says that it's all X such that means it fits the criteria that falls next. The criteria is that we have numbers less than 5. Are all those numbers less than 5? Yes. But notice it doesn't include like negatives, right? It doesn't include fractions or decimals. It doesn't even include 0. So I need to have a way of describing that to exclude those things. And the way to describe that is natural numbers. So natural numbers are the numbers that children very first learn starting to count with. So when you learn natural numbers, when you learn to count, what's the first number you learn? 1. You don't learn 0, right? Like it doesn't take a lot to add 0 into your sort of image of numbers later on, but you don't start there. You start with the number 1 and you build on from there. So what we're going to do next is we're going to actually look at some of the symbols that are used in set builder notation. And I'm first going to look at some of the symbols for the number systems themselves. So I mentioned to you natural numbers. So if you write a letter N with 2 lines on the left, this is what is meant to be the natural numbers. And natural numbers are the counting numbers. So I'm going to put counting in parentheses. And they're numbers like 1, 2, 3, and so on. These are the natural numbers. Next, as you sort of expand your ideas of mathematics, somebody asks the child something along the lines of, if I have 3 apples and I take 3 apples away, how many apples do I have left? And you need another number. That new number is the number 0, right? Once you include the numbers you already have plus the number 0, those numbers are called the whole numbers. So it's the same list, but it starts at 0 instead. Okay? We're going to be doing a lot with whole numbers. All of Chapter 3 is based on the whole number system, 0 and up. So for the most part, it's everything that you're going to be doing all the way up to somewhere in about 3rd to 4th grade when students are first encountering fractions. Yes, they do encounter them at very early grades, very minimal kind of things, but they do encounter them at about 3rd to 4th grade, depending on the curriculum that the school system is using. All right. We're going to expand this not necessarily in terms of curriculum, but in terms of the way that we can add things to it and still sort of be self-contained. So I'm not going to go to fractions next is my point, even though the school system would. What I'm going to do next is sort of, I've thought about sort of the numbers like this direction on the number line from 0 and on, and I want to go this direction on the number line. And these direction of numbers over here are the negative numbers, right? So if we expand in the other direction, these are called integers. And I'm going to tell you what the letter is just a second to call them that. It's not I. The integers, and I'm going to put a dot, dot, dot at the beginning, would be the negatives of all the numbers that I just listed. Okay? I have a feeling your book actually uses I. And while I typically like to do whatever a book does, I can't do that with you because that is not typical notation. I've never seen another book do that before in my life. And there's a very good reason, I'll mention it in a second, but the letter that is typically used for integers is the letter Z. So it's a Z with a double line through the middle is what it ends up looking like. This is integers and has to do, I should probably look up what it is, but it's the Latin word for integers. That's where the Z is coming from. Okay. Now we're going to expand to the fractions. And what we're going to have are called the rational numbers. So the rational numbers would include, and I can't write it in a closed form, like this listing method works really nicely for what I just did before. It doesn't work so well beyond that. So we're going to actually write down sort of a description in words about what this is. So these are all fractions. And I'm going to put slash decimals. Fractions and decimals are just ways of representing numbers that are the same, that are different, but it's the same number. So these are fractions and decimals. Now, it includes all the whole numbers and things we did before. So consider and all of, let me say plus, all of the above. Plus all above. And saying plus all above is a little bit unnecessary, but it does feel awkward to say, for instance, the number 3 is a fraction. But really, it's because we can write it as like 3 over 1. So that's what we're talking about. And it's not all fractions and decimals. They have to be fractions and decimals of integers. So you can have things like 2 over 3 and 7 over 12 and negative 4 over 29. You can have all of those. You can also have things that look like they're decimals over decimals because they have the ability to be changed into an integer over an integer. So let me write down an example of what I'm saying that. Let's say it's 1.7 over 2.3. Well, that doesn't have integer over integer, but if I multiply by 10 on the top and bottom, I have the ability to change it into something that does. Okay, so that's what makes this work. The thing you don't have here is you don't have some of the numbers that you encounter in later middle school to high school. They typically show up in geometry concepts the first time you see them, things like pi, right? Pi is an irrational number, okay? So I'll come back and write down what the notation is for that in a second. But you can't include anything irrational in this. And irrational numbers are, and again, I can't write it in any other way, but I'm just going to give you some examples. An example of an irrational number is pi. Also irrational are anything that's square roots where you can't simplify them, like square root of 2. And one of the ways you've probably heard people describe irrational numbers before is that they have decimals that keep going and don't repeat. So you can kind of think of it that way too. Another way to describe them is they're immeasurable. Like I can't stop the decimal and actually measure it the way that I would want to with a decimal form normally, okay? So these are irrational. All right, so rational numbers are actually written with a Q. And as much as I wish that irrational numbers was the I that I mentioned before, there's actually not a convenient notation for that. It's actually written, let me stop. Let me come back to that in just a second. There's one more type. The last number is real numbers, and that includes everything above. So that one's written as R for real. And then irrational is actually written as R and then remove Q. I have a couple other notations to write in here, maybe just one more notation to write in here. So I'll shrink my screen in just a minute. But let me talk about where the Q is coming from, because it's not Latin anymore. The word Q comes from the word quotient. Quotient means division, right? If you're asked to find the product, the sum, the quotient, the difference, those are all the basic terms for addition, subtraction, multiplication, and division, but not in that order as I just said. Quotient means division. And a fraction is division, right? So when I wrote 17 over 23, I'm really saying that 17 divided by 23. That's what fractions mean, so that your quotient is Q is coming from the word quotient. And then R is, of course, real numbers, okay? So there's not a good way, not an accepted commonality anyway for writing irrationals. The majority, this class that you're in is going to do natural numbers, whole numbers, and integers. That's all that we're doing in this first 5 chapters of this book. The rational numbers actually show up if you're doing proportional and statistical reasoning. So fractions, decimals, we get into those kinds of things. And you do get some of the irrational numbers in geometry and measurement. And I know many of you have taken geometry and measurement, and you probably saw pi in there, right? Because you're doing things with geometry. There's one more piece of notation that we are going to see used in set builder notation. And it looks like a curly E, like this. It is not a box E. It's not your E's that you're used to. Those have other meanings. I should mention actually irrational. There is an E that shows up here too. You might have seen that in high school. Like E is about 2.718. Typically shows up in about algebra 2. This isn't the E we're talking about, right? We're talking about this E down here at the bottom. And this E here at the bottom means is an element of. Okay. Now we talked about what elements were. That was the first thing we did. We said elements are just these individual objects in the set, right? Just individual objects that are in there. That's elements. So we have a notation that looks like this. So what do you suppose? I won't write it down because I think we can do it without it. But what do you suppose? That doesn't look very good at all. What do you suppose it is when I put a slash through it? It's not an element of, right? It's not rocket science, right? Draw a slash through anything, it means the word not. It's a negation kind of comment, right? Yeah. So we're going to take a trip back one time into this note on the board on the slide before, and we're going to write this one other way. Now, the first part's the same, x such that x is less than 5. That's not any different. But notice at the end here it says x is a natural number. That's really long to all write out. I mean, it is. It really is. There is a shortcut notation for it, and it looks like this. X is an element of n. This is telling you that this x, i.e. these numbers who are less than 5, are natural numbers. That's what the notation is telling you. Now, every now and then I get people getting really frustrated in math because they're like, why is there so much notation? Why is there? Because it's faster. And you guys do it all the time. Have you ever used shorthand notation when you've texted somebody? Every single time you text, you probably do something in there, right? Not every time. But with any thread that you've got going on, it's all over the place, right? That's what this is doing. It's just shorthand notation for something else. It's got a learning curve, right? It's the same thing that happens whenever you start using some other new texting shortcut or whatever, is that the first few times you use it, you're thinking the words out loud, right? Like when I type LOL, I do not think laugh out loud. But I do LOLs a lot. I know, I'm old, but that's what I do. Okay, but I don't think it anymore, right? I just type LOL and I think LOL. I don't think laugh out loud. But when we first started using it, however many 15 years ago, I probably did. Every time I typed it, I thought to myself the whole word. That's what's going on here. Okay, so let's take a look then at equal sets. I'm skipped one. I'm so sorry. Example 1. Here we're going to write the set of all natural numbers less than 5 using, that's the one I already did. Well, we'll practice it again. Let's just change it a little bit since I mentioned this one before. I didn't mean to use the same one. Let's say more than 6. Let's do that. We'll say more than 6 so we have another example. I apologize. Okay, so if we're doing the listing and roster method and we want all the natural numbers more than 6, what is the first natural number more than 6? 7. Fantastic. And then what's the next one? 8. And 9. And 10. And it keeps going on. How long? To infinity, like forever, right? It never stops, right? Infinity and beyond, like that kind of stuff, right? It's not going to end. This isn't a very good example of a listing method, but if you were doing this and trying to do so, the best thing you could do at this point would be to do this, right? ... Close the curly brace. However, set builder notation for that note really works very well. So what we do for set builder notation is we start the curly brace, we write an X and a such that. All that's the same. But it told us that X is greater or more than 6. Well, I have a notation for that. X greater than 6. I can't stop there though, because if I stopped there and I did a curly brace like right there like that, it would include some numbers that I didn't mean to include. What would be included if I stopped right there and didn't specify? 6 what? 6.1 would be included, right? It would. 2 pi would be included too, by the way, huh?
So every decimal value would be included.
Yeah, every decimal, every irrational, everything bigger than 6 would be included. So we want to make sure that we specify the kind of numbers we're talking about. And these kind of numbers in this description are natural numbers. So we're going to put the N.
Well, what stops you from using whole numbers?
Nothing, and it would be equally correct. You could use whole numbers there. You could use integers there. You couldn't use rational or real. Very good point. Thank you, Savannah. Okay. So equal sets. So these are very interesting because there's going to be 2 descriptions on this slide. One's on this page of yours and one's on your next page that talk about sets that we would maybe have thought that the language meant the same thing. Equal sets are 2 sets that contain exactly the same elements. So if I talk about my family, as in me, my husband, our children, right? If I talk about my family and my husband were to talk about his family, because we share all the same children, we'd be talking about the same people. Agreed? Those would be equal sets. Now, equivalent sets, which equal and equivalent are awfully similar words, are not going to be the same sets. In fact, they hinge upon this definition that's in between, called one-to-one correspondence. So one-to-one correspondence is a pairing of elements between 2 sets, such that each element of one set is paired with exactly one element of another set. So this is the idea. We've got a little space at the bottom of your page of having sets that are the same number of elements. So I'll write a very boring example. I've got a set with the number 1, 2, 3 in it, and I've got a set with the letters A, B, C in it, and somehow I pair these guys up. Everybody has a partner. Okay? That's one-to-one correspondence. One-to-one correspondence in my history involved my mom and her best friend. So growing up, my mom had a best friend. My mom's best friend had 3 kids. My mom had 3 kids. This was fantastic because when we got together, everybody had a playmate, right? You could pair up because groups of 3 do not work. Have you ever experienced this? If you haven't, once you're around kids, you're going to know it real quick. I have children, right? And when we are at the lake, like we were over Labor Day, if there's an odd number, it's always girls, by the way. The boys do just fine. If If there's an odd number of girls, there's going to be drama. It's not going to go well. But if there's an even number of girls, it usually does. So this one-to-one correspondence tends to work really well. So when I have this one-to-one correspondence, what I have are something called equivalent sets. Equivalent sets just means that they have the same number of elements in them. Doesn't matter what the elements are. There's just the same number in one as there is in the other. Okay? Same number as one as there is in the other. Now, if you think back to my example with growing up, and there was 3 of us, myself, my sister, my brother, and this other family, they happened to have 3 girls. There's a variety of ways we could pair up, right? Now, what we normally did is the oldest paired up with the oldest because they kind of had the very similar age structure all the way down. But that's not the only way that could have worked, right? Like I could have, as the oldest, hung out with the one that was the youngest or something like that. There could have been some sort of different pairings going on. So that's what's actually being talked about here. If we have, in this case, 6 elements, how many different groupings could we make? And so I want to do an example with dating because it works really well. So let's pretend for a moment that there's some sort of a party and there's dancing involved or whatever. Okay, so nobody is singularly attached to anybody else, or this doesn't sort of sound very nice, all right? So there's 6 young men and there's 6 young ladies that come, right? How many different pairings can happen? What happened? I don't know, just some sort of noise. Okay. All right, well, we have 1, 2, 3, 4, 5, and there's 6. We'll say young men first. And over here, there's 1, 2, 3, 4, 5, 6 young ladies. Well, young man number 1 could be dancing with lady number 1, or lady number 2, or 3, or 4, or 5, or 6. There are 6 different people that he could be dancing with, right? Okay, assuming that there's no girls dancing together, boys dancing together, okay? So as long as we're distinguishing the sets independently like this, there's 6 different people that person number 1 could be dancing with. However, once that person is paired up with somebody, I don't care where you pair him up, let's just go straight across, person number 2 does not have 6 different people they can pair up with now. One of them's already got a dance partner, correct?
Yeah.
So person number 2 has how many options that they could be dancing with? 5. And once you decide, whoever they have, I didn't mean to put number 5 as though it's 5, their answer, just paired up with somebody. So person number 1 had 6 options. Person number 2 has 5 options. So how many options does person number 3 have? 4 options, right? There's 4 people left that he can choose from among to dance with. How about person number 4? Oh, I should put him with somebody. Let's just put him straight across 2. Yeah, person number 4 has 3 options. How about person number 5? 2 options. Person number 5 has 2 options. And person number 6 then would have how many? 1, because there's only 1 person left that's not dancing yet. Okay, so we have some sort of pairing going on. Random, it doesn't really matter. But there's these numbers of options they have based on how many people are already paired up. Agreed? Now, the way that we figure out the total number, or how many, like this says here, how many of these there are, is that we multiply the ways that each of these had options to be paired. We'll see more about this later. If you've taken proportional statistical reasoning, we talk about this idea as well in a different chapter there. It comes up throughout mathematics. It has a name. It's called a permutation. If that sounds familiar, it's great. If it doesn't, it's fine. But what is 6 times 4 times 3 times 2 times 1?
720.
720. There are 720 different correspondences. It's a wonder that anybody's danced with anybody. They got so many choices, right? It's a lot of options. It's a lot of options. Now, what you're going to see happen in some of your homework and group work questions when we get there is they're going to give you, 5 pairings, 5 and 5 or 4 and 4 or something like that. But they're going to tell you an additional condition. It's going to look something like this. There's 6 men that come to the party and there's 6 ladies that come to the party. But one couple is dating. And it would be highly discouraged for them to date somebody or to dance with somebody else when they're at the party. Agreed?
Yes.
Probably would not go well. Okay? I will say Tango. If you go to Tango, this is not the case. You dance with everybody there, and you dance with them 3 times. It's very strange. I'll tell you how I know that later. But, okay, so in a normal situation, 6 of them show up. 1 couple is dating. That means that there's only 1 person that they have the option of, right? And then there's 5 people in each category that we have this situation going on with. So person number 1 has 5 choices, and person number 2 has 4 choices on the down line, okay? So if there's already some sort of a pairing happening, then there's not 6 options that person number 1 has. They only have 1 option, right? Leave with the one you came with kind of thing, right? Like that's the deal. Savannah.
So what would happen if there were 5 girls and 6 boys?
That wouldn't work at all because there's not a 1-to-1 correspondence. The 1-to-1 correspondence means that we have the same number of people in each grouping.
So we won't see questions.
No, you wouldn't see questions like that. Yeah. Okay, now, cardinal number is simply the number of elements in the set. Okay, how many it is. So, the way that is written is like this. N meaning number of, right? S is the elements in the set S. So if I were to talk about, let me see if this is an example I've written down. No, it's not. Okay. If I were to talk about the number of people that live in my house right now, N of Hans family in the house would be 6. Okay. If I talk about the number of people that are there on Christmas morning, assuming nobody's working, that's actually the number 10, right? Because I have some adult children that have moved out and that will be back, that sort of thing. A set is called finite if its cardinal number is a whole number. If it can be counted, for the lack of better terms. It's not exactly a definition because it doesn't fit very good for real mathematics terms. But for what we're talking about, it's okay if you think about it that way. There's a fixed number, right? It's finite. The number of people in this room, it's finite. It's definitely not infinite, right? It's finite. I can count you up and I can give this group a number. An infinite set is a set for which the cardinal number is not a whole number. So that's what was happening when I was talking about rational numbers. And it happens for irrational as well. So rational numbers is all those decimals and fraction numbers, right? And irrational would include the square roots and the pies and things like that. There's no good way to write them all out. In fact, there is no way at all to write them out, right? Because they're infinite. There's no way to write them out. Not only that, but it's actually called uncountable. While, let's say natural numbers are also infinite, right? Like came a point over here on this example where I had to put the ... on the end and it continues on forever. That's infinite, right? I can't count up how many of them are in there. It's actually called countably infinite. This is just bonus for your dollar today. But it's infinite, okay? It's an infinite set. It's never ending. It never stops. So this is infinite as well. And then the last one is the empty or the null set. So the empty or the null set is a set that contains no elements. And it has a cardinality of 0. Okay, if I counted the number of objects, for example, the number of people in my office right now, or just not even the number, it's just the people in my office right now. Well, there's no one in my office right now, I assume, unless somebody broke in. Let's hope not. There's nobody in my office right now. That's a null set. Because if you were to try to count the number of people who are there, you'd get the number 0. Now, null set is written one of 2 ways. Either a 0 with a slash through it. Please note, this 0 with a slash through it has a notation that means something that's not just 0. This is not the number 0. This is the symbol for empty set. So if you are someone who likes to write your zeros like this, you must stop right now. This means something different. It has another notation as well. When that notation has another meaning as well. When you're working in algebra, it means no solution, which is another reason you shouldn't make your zeros with slashes through it like that, is because it actually has another meaning in terms of an algebra context. But this means empty set. The other one, which is kind of friendlier, is curly braces with nothing inside. It's a set and it's empty, right? It looks just like what we're saying it is, a set with nothing in it. Okay. I think let's do one example, and then we'll come back to it and we'll relax next time. All right, we're going to find the cardinal number of the following sets. So cardinal number just means how many are in them. We'll do letter A, which is set A. We have all the numbers that start at 9 and go to 99, and we've done this before. We did this for Gauss's method when we were trying to count lists of numbers. Do you remember how we figure out how many are in this set?
Take the beginning number and add it to the end number.
Close. It has to do with the beginning and the end. That part's right. There's a subtraction feature, not an addition. That one's a little bit off, yeah, but we got the idea. Okay, so the notation looks like this. Number of items in set A. We are going to subtract, but we don't subtract 9. What do we subtract? 8. We subtract the number before the one we're working with when the situation's like this. What's 99 minus 8? 91. So the cardinal number for set A is 91. And we will pick back up with this on Monday with part B.